So, hello everyone. Welcome to the week 5 of problem solving session for the course on computational complexity. So, the topics for today are the randomized complexity classes. So, we'll look into majorly three classes: RP, BPP, and ZPP. So, let's start by defining what these classes are. So we say that a language L is in RP if there exists a probabilistic polynomial time machine M such that whenever X is in the language, the probability that the machine M accepts X is at least half, and if X is not in the language, then we are always going to reject X. So M rejects X, or let's say the probability that M rejects X is equal to 1. So what that really means is that in one case, when X is indeed in the language, there might be some error that our algorithm or machine makes, but in the other case, when X is not in the language, we are always going to be correct. So similarly, natural question is, can we reverse the situation? That is, if X is in the language, can we always answer correctly, and when X is not, can there be some error probability? So this class is what we call co-RP. So co-RP is, you say that a language is in co-RP if there is a probabilistic polynomial time machine M such that whenever X is in the language L, the probability that M accepts X is equal to 1, and when X is not in the language L, the probability that M rejects X is at least half. Okay, so so these kinds of algorithms are called one-sided error algorithms. Okay, and we can ask whether there can be machines that make errors on both in both the scenarios. So instead of having a guarantee in one case, what if we have machines that are allowed to make error in both the cases? So we define our language BPP, which is called bounded probabilistic polynomial time. If there is a probabilistic polynomial time machine M such that when X is in the language, the probability that M accepts X is at least 2/3, and when X is not in the language, the probability that M rejects X is at least 2/3. Okay, so notice that here, while defining the one-sided error class, we use this error probability of 1/2, whereas here we are using success probability of 2/3. So we'll see later why it is the case and why are we not really calling it half. Okay, so this is called two-sided error algorithm. So that's the definition, and clearly can be seen that if L is in RP, then L is indeed in BPP, and similarly if L is in co-RP, then L is in BPP, because BPP is just a relaxation where you are allowed to make error in the other case as well, whereas the RP and co-RP are stronger guarantees. So the picture looks like this. We have class BPP and we have RP sitting inside it, and we have co-RP sitting inside it, but we don't know whether RP is equal to co-RP. So this is similar to the NP versus co-NP problem. We don't know whether they are equal, but it's clear that P is sitting inside this. Okay, so this is just a clear from the definitions, because P does not even make any error. So yeah. Okay. And the other point to note here is that there are two ways to view this probabilistic Turing machine. One is that you can think of the machines having some probabilities associated with it. So, so for example, at some point it branches from a state A to state, say, B, C, and D. Then non-determinism simply says that you are allowed to make any one of these choices. But what probabilistic machines have additionally is that they have some probabilities associated with it. That is, say, with probability 1/4, it will go to the state B. With probability 1/4, it will go to a state D, and say with probability half, it will go to a state C. So so we have these kind of additional probabilities that are associated with the state um, with the transitions, and so that is one way of viewing it. That is, think of it as a machine with probabilities on every transition. The other way to view it is that think of it as a deterministic machine where we're going to make we're going to run it on all random seeds, and then look at the majority of them and answer otherwise. So likewise, so let's say the other way would be that M is a deterministic machine which is going to run X on each R. So it's going to go over MXR for all R, and then look at the answers for all of them, and then take a majority. Okay, so that is another way of viewing it, and this is a probabilistic machine, and both the notions are equivalent. It can be shown that they are equivalent. Okay, but we'll not get into the details right now. So okay, so these are the basic definitions, and we'll move on to the questions. The first question says that if okay, so just to give a picture, so we have this picture that we know that NP P is contained inside NP, but we don't know um, whether these are equal or strict. So this is an open problem that we know. The other major open problem that we have is whether BPP is equal to P. We know that P is inside BPP. That's something we saw already here. So P is inside BPP, but we don't know whether they are equal. And and in fact, we don't know whether NP is equal to BPP. That is another major big problem, big open problem. Okay, so okay. Okay, so the what the question really says is that, let's say we know answer on this side. Let's say we knew that P were equal to NP, then that would imply that BPP is indeed equal to P. So yeah, so how do we show that? We'll use this this theorem that we know that BPP is contained inside sigma 2P intersection pi 2P. Okay, and yeah, and notice that what is sigma 2P? Sigma 2 is essentially a there exist for all statement, or you can think of it as an NP to the NP. It's the set of all languages that have an NP, that have a non-deterministic machine that runs in polynomial time, given access to the SAT problem. Okay, so so this is what we know. But now that NP is equal to P, what really happens here is that this boils down to NP to the P, and this further boils down to P to the P, because we know that NP is equal to P. So so the non-deterministic machine can as well be replaced by the deterministic machine that runs in polynomial time, and P to the P is nothing but P. So therefore the polynomial hierarchy sort of collapses to this level, to P, and therefore BPP in particular. Similarly, you can show that indeed pi to P also collapses to P, therefore BPP is equal to P. So therefore what we have shown is that if NP were equal to P, then the BPP would be equal to P. So yeah, okay. So just to summarize, what we did was we used this result that we know that BPP is contained um, in the sigma to P intersection pi to P of the polynomial hierarchy, and we know that sigma to P is nothing but NP to the NP class, and then we replaced um, the NPs with the deterministic machines, which gave us that BPP is equal to P. Okay, so okay, so let's move on to the next question. So okay, I think there's some lag here. Okay, okay. So yeah. So notice that we saw that there are these languages inside BPP which we called RP, where there's these languages that are sitting inside are making one-sided errors, whereas BPP as a whole is allowed to make errors on both the cases. Okay, so and this was, to be precise, this was the definition of RP that we defined. In the yes case, it's correct with at least half probability. In the no case, it's always correct. Okay, whereas when we define BPP, we did we yeah. So coming back to this point, when we defined okay, I'll wait for the screen to refresh. Okay, okay. So when we defined this class RP, we had this probability, this uh, correctness probability of half fraction, and when we defined co-RP similarly, we had this correctness probability of half fraction, whereas in the case of BPP, we insisted that the correctness probability be 2/3. Okay, so um, yeah, so the okay, so the question is, can I make it half? So if can I define BPP to be half, and instead of 2/3, and will it still be fine? Okay, so let's see why this cannot be done, and why this 2/3 is what we generally work with. So the reason is that, let's say I have my RP. Okay, okay, I don't know. I'll maybe reshare the screen again. There seems to be some lag in the um, visibility. So okay, so let's see the RP algorithm. Um, okay. Okay, so okay, let's see if this works. I've started the screen share again. Okay, so how did we define this RP? If X is in the language, then the probability that m accepts x is at least half, and if x is not in the language, then the probability that m rejects x is equal to 1. Okay, so let's say I don't want to work with, like, I'm not very happy with this half probability. What we'll do is I'm going to run this machine m again. So this is what we call the standard amplification technique, where what we'll do is on input x we're going to run m on x for k many times. Okay, so these are our independent runs, m1, m2, and so on up to mk. So we're going to run it on the same machine m on the same input x but k many times. And notice that because the machine is a probabilistic machine, on the same input it may say yes, it may say accept x, it may also say reject x. So let's say it does say accept here, it says reject here, then it says, let's say, accept, and then let's say accept. Okay, so okay okay so notice that if x were not in the language, so let's analyze this in cases. So the simpler case is that x is not in the language, then by the definition of our machine we know that m is going to reject x with probability 1. So if x were not in the language, these machines, all of them, would have said reject, 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 and so on. So in that case we'll go ahead and reject it. Okay, but if any mi says accept, then we are going to accept. So that is the idea. So we'll look at all the runs. If any one of them says accept, then we are going to accept. If otherwise, in all the cases, we are going to reject. So what is the correctness probability now? So if x were indeed in the language, or let's say x is not in the language, then it's always going to reject, and therefore we are also going to reject. So this probability is not affected. So the probability that m rejects x is still 1. But if x is in the language, then what is the error probability? The error probability is that, okay, x is in the language, but all of them said reject to me, and therefore I ended up rejecting. So what is the error probability that we made? So if x is indeed in the language, but we made an error, so what is the probability that m makes error? So it can only happen if m1 also said rejects, and I'll say multiplied, and okay, maybe we'll write it like this: m1 made an error by saying that it rejected, makes an error, and m2 makes an error, and m3 makes an error, and so on. All the machines mk make an error. This is same as probability that m1 makes error times probability that m2 makes errors, and so on, times probability that mk makes error. Okay, and what is the probability that a machine makes error? Since the success probability is half, it's going to make an error with probability less than half. So this is, and these are all independent runs. The output of machine m2 has nothing to do with output of machine m1. So these are all independent probabilities, independent events. Therefore it's okay to multiply all of them. So we're going to do this k times, and that gives us 1 over 2 to the k. Therefore the probability that when x is in the language and we make an error has boiled down to very negligible value, which is say 1 over 2 to the k. So if I choose k to be polynomial, because I have a probabilistic polynomial time machine, so I'm allowed to make polynomial many runs, then this error probability is very negligible. Okay, so So then what is the probability that m succeeds is at least 1 minus probability that it made an error, and that is at least 1 minus 1 over 2 to the p of n. So just by um, running the machine several number of times and defining the acceptance and rejectance conditions appropriately, what we've done is we've taken a machine m whose success probability on instances that are in the language is half, at least half, and success probability over the no instances 1. We have modified it into a machine m prime that is going to succeed with a very large probability when x is indeed in the language, and um, and still maintain the guarantee that if x is not in the language, we will never make errors. Okay, so so this is the nice thing that we could do about RP. So even though we started with a machine with a probability error probability of half, we could bring it down all the way up to a very negligible value. Now the question is, can we do the same thing for BPP? Okay, so that's why it really does not matter, by the way, in the case of RP, whether you choose half or something larger than that, because even if you take half, just by running it a few number of times, you can actually bring the error down to a very low value, so doesn't really matter. But in case of BPP, um, what happens is, let's say that we defined it with half. Let's say we did that. So if x is in the language, the probability that machine accepts x is at least half, and if x is not in the language, then the probability that m rejects x is at least half. So let's say we defined it like this. Okay, then what's going to be the problem with this? So can I do the same thing? So let's try an amplification technique, which is basically that we're going to run m on x for k times, and then we can't do something that we did earlier. Like, we can't say that if there is at least one accept. So what we did earlier was that if there is one accept, then we are going to accept, otherwise we are going to reject. So this is something that's not going to work for us, because now we are making errors in both the directions. So what is a obvious thing to do here? Because it makes error with probability half in both the cases. Natural thing to do is that you run it k many times and take a majority of the outputs. So let's say m1 says accept, m2 says reject, m3 says accept, and so on, and mk says accept. So let's say that more than half of them, so let's say if majority of the machines say accept, then we are going to accept, otherwise we are going to reject. Okay, so this is the most natural amplification technique here. Now the question is, what happens to the error probabilities? So notice that if, so let's do that, let's do the count. So okay, so if x is indeed in the language, okay, if x is indeed in the language, the probability that m1 makes error is half, bounded by half, m2 makes error is bounded by half, and so on. And when you take the majority of them, the probability that we will eventually end up accepting is again half, or the probability that we are going to reject is again half. So why is that? Because what is the probability? So this is an exercise that simple exercise that one can try. What is the probability that the majority of m1 to mk accept, and what is the probability that the majority of m1 to mk reject? So this will turn out to be again half and half, because there's really no correlation between the output of m1 to mk. So with half probability it's going to say accept, with half probability it's going to say reject. So so overall the majority is going to be half with accept with half probability and reject with half probability. So therefore, even though we have run mk many times, it has not really helped in getting any confidence in the answer. So the probability that we will end up accepting m accepts x is still going to be at least half, and if x were not in the language, by the same analysis, the probability that m rejects x is again going to be at least half. So this amplification that we did is useless, because it didn't fetch us anything. We are still in the same situation. So this doesn't work. But let's say I chose something more than half. So let's try with 1/3. Okay. So let's say that we will try with the current definition of BPP, that if x is in the language, then probability that m accepts x is at least 2/3, and if x is not in the language, then the probability that m rejects x is at least 2/3. Okay, so let's use the same previous amplification technique, which is that run mk times on x. These are independent runs, so m1, this is the first run, and so on. These are the k runs. And now let's and do the same thing. Take a majority. If majority accept, then we are going to accept, otherwise we are going to reject. Now let's analyze the probabilities. So if x is in the language, okay, what is the probability that we made an error? So probability that m errors makes an error is that majority of MIs made an error. Okay, so this could happen if all k many machines made an error. This could happen if k minus 1 many made an error, and so on, all the way up to k by 2 minus 1. Okay, so if we analyze, let's say try to analyze that, what is the probability that all, so these are union, by the way, so either this or this and so on. Okay, so let's analyze the first one. What is the probability that all the k machines make an error? So first machine makes an error with 1/3 probability, second machine makes an error with 1/3, and so on. This is all together 1/3 to the k. Okay, and let's analyze the second one. What is the probability that k minus 1 of them make an error? So this could happen if any k minus 1 of these k machines make an error. So there are several choices or subsets that one can think of. So in fact, these are k choose k minus 1 many subsets. The probability that one of them is correct is 2/3, and the probability that all the rest of them are make an error is 1/3 multiplied k minus 1 many times. This is nothing but k times 2 over, or 2k times 3 to the k, and so on. So what happens is, all of them are going to have this 3 to the k in their denominator. So if k were polynomial, this error probability is going to be very small. Even if we are going to add up these terms, the numerators are really small compared to the denominator. So the error is going to reduce by a large fraction. This is simply happening because we started off with a fraction that is greater than half. So there's nothing special about 2/3 here. Anything greater than half will fetches the same amplification, but uh, we sort of stick to this because we just wanted a fraction um, larger than uh, larger than half, so there's a simpler fraction to come up with. So there's nothing um, I mean nothing specific about it. You could have chosen any other fraction. um, yeah. Okay. So to conclude, what we really did is that we tried to understand the definitions of these classes, that RP was defined with a half probability, um, and likewise for the co-RP, whereas BPP was defined with error of 1/3. So we saw why is that so, and why do we make that choice, and why half doesn't work for BPP. Okay. So hmm, okay. Okay. So I'll move on to the next question. So we're given this complexity classes, um, LP, P space, EXP time, and um, yeah, and we definitely know that um, EXP time P and L. So this is the hierarchy that we have, and the question is, where does BPP fit in here? So we want to give the position of BPP in this hierarchy. Okay. So okay. So notice that one thing that we already saw was that we have BPP here and RP here, co-RP here, and we had P sitting inside this. So we clearly know that P is contained in BPP. Of course, L is contained in P, but we want the tightest bound that we can give, so that is P in this case. So we know that BPP is going to lie somewhere here. Now the question is whether BPP is contained in P space, or we don't know that, or whether it's contained in EXP time. So this is something that can be okay. So that can be shown. So in fact, this is something that we saw earlier. So it can be shown that BPP is contained in P space. So how do we do that? We know that if X is in the language, by definition of BPP, probability that M accepts is at least 2/3, and if X is not in the language, then the probability that M rejects is at least 2/3. So what one can do is that we can now use the equivalent definition of BPP, which says that you can think of M as being a deterministic machine, and so this is the definition 2 that we saw, that M is a deterministic polytime machine, and what it does is that it is going to run MXR for all R, and if at least 2/3 of them say accept, then we are going to accept, otherwise we are going to reject. So this is the this is what you can think of it doing internally. So natural thing would be that we're going to simulate this thing in our P space machine. So what we'll really do is that we're going to have some counter here. So let's say all choices of R would be, say, all zeros. These are the random seeds, 0 0 0 1 all the way up to 1 1 1 1 1. Okay, and these are the length of this is polynomial. So there can be a polynomial some P of n space that is that is to keep track of what is the random seed that I'm currently working with. Then we're going to run our machine name on input X and random bit R. So this is since P is a polynomial time machine, it's going to take Q of n space, which is again polynomial, and then we're going to keep a counter here which says if it accepts, then we're going to increment the counter. Okay, and this can again be done in P of n space. Next, for the next simulation, what we'll do is we will reuse this space and move our counter and go to the next random seed, and reuse the space again for this new random seed, and run the machine M on X and the new random seed using the same space. And again, this can be done in Q of n space. If it accepts, then we're going to increment the counter, otherwise we're not going to change it, and we keep on doing this. So for every random seed, we are going to reuse the space here and reuse the space for the execution of the machine M on this input, and we're going to keep track of the number of times that we accepted. At the end, when we've run through all the seeds, we'll look at the counter. If it's greater than 2/3 of the fraction, then 2/3 of the fraction, then we will accept, otherwise we will reject. So all of this can be done in polynomial space because we are reusing the tape. Okay, so so I went through it a little faster because we've seen this argument already. So we know that BPP is contained in P space. So by transitivity, BPP is also contained in EXP time, but we are looking for the tightest bounds here. So P space and P, these are the tightest bounds that we know for the given among the given options. So BPP is contained in P. Contains P and is contained in P space. This is the final answer. Okay. Okay. So I'll move on to the next question. Okay, so this is an interesting one. So what we want to show is that, okay, just to recall the picture, we know that okay, we don't know whether NP is equal to BPP. We don't know the containment in any direction. So we don't know whether NP is contained in BPP, or is it that BPP is contained in NP. We don't know any of these. What the question says is that, let's say we knew that, so we have our BPP here. Let's say we knew that NP was contained inside BPP. Okay, and we know that RP is contained inside BPP. That's something we saw. Then what it really leads to is that RP is equal to NP. So how do we show that? Okay, so what is the proof idea? So we want to show that NP is equal to RP. So notice that RP is this is something we saw earlier in the course. So we know that RP is contained inside NP. Why is that? Because it says that if X is in the language, then probability that M accepts is at least 2/3 and at least half. And if X is not in the language, then the probability that machine accepts X is equal to, rejects X is equal to 1. So what this really means for us is that the probability that M accepts X, it means that among all the computational paths in the computational tree, at least half of them led to accept. So what that means is that there exists a path that leads to accept. Okay, and that is our acceptance condition for NP. So therefore our machine M prime for NP will also end up accepting, because there exists a path. There are at least half fraction of them. That's irrelevant for us. We just need one path, so our NP machine would end up accepting. What this sort of means is that if X is not in the language, then all of these computational paths are going to lead to reject, and that's a reject condition for NP. So our NP machine is also going to reject. So indeed, if X is in if a language is in RP, then it's also in NP. So this side of containment is something we know. So it suffices to show that if NP is contained in BPP, then NP is contained in RP. Okay. So how do we do that? Well, use our NP complete language that we know here. So we know that if if SAT is in RP, if it can be shown that SAT is in RP, then it implies that NP is contained in RP. This is because this is the hardest problem that we have in the NP in our NP set. So so all the other problems can be reduced to SAT. So if SAT has an RP algorithm, that indeed means that every language in NP has an RP algorithm. So it's sufficient for us to show that if NP is contained in BPP, then SAT is in RP. Okay. So okay. So what does this really mean? So let's say that SAT has a BPP algorithm. Then what it means is that if phi is satisfiable, then this probabilistic polynomial time machine M is going to accept with 2/3 probability, and if phi is not satisfiable, then the probability that M rejects is going to be at least 2/3. Okay, so this is what it means to say that SAT has a BPP algorithm. Now what we want to do is that we want to get an RP algorithm for this, and the key difference here is that, so the key difference, I'll just write with a different color here. So what we want is that we want that when phi is satisfiable, we want that the probability that M accepts is at least half. So this is already satisfying that condition. And when phi is not satisfiable, we want the probability that M rejects to be 1. So this is something that we need to work on. So we are not happy with this 2/3. If it is not satisfiable, we don't want to make any error. Okay, so how do we do that? So this is where we're going to use the idea of self-reducibility of SAT. This is something that we've seen earlier in previous tutorials. So we know that self-reducibility of SAT. So I'll write the main idea. The main idea is going to be that I'm going to somehow find an assignment A for phi, which is a satisfying assignment with good probability. So I'll not define what good is right now. Okay, so how is that different from what we were doing earlier? Instead of saying that okay, there is a satisfying assignment with a good enough probability, I'm going to find that. So this is the key part. So we're going to find it explicitly. Okay, and we're not saying that this is actually going to satisfy the formula phi. All we're saying is that with a good enough probability, it's going to satisfy the formula phi. Now why do we need this? Because if I have this satisfying assignment A, or probably satisfying assignment A, then what I'm going to do is that this is the key part, that I'm going to manually check if A indeed satisfies phi. So how do we do that? I have this formula phi and I have this assignment A, which is say 0110, some 01 assignment, and I'm just going to run it on the formula and find out whether it's going to say output 0 or 1. So if it accepts, or if it says that okay it is, so if it satisfies, so if phi of A is equal to 1, then we are going to uh, say that yes, the formula is satisfiable. Otherwise, if phi of A is equal to 0, that is A does not satisfy phi, then we are going to say reject. Okay, so there are two things that we did not, okay, one thing that we did not specify at the moment, that is how do we find this assignment which with good probability is a satisfying assignment for phi if one exists. Okay, so that is something that we didn't define at the moment. We'll do that, but let's try to understand the main idea of why we're doing this. So if I have this assignment, what I can do is I can actually check it and tell whether it's satisfying assignment or not. So this actually helps us get this probability, this error that we were making in the no case, make this error all the way down to 0. So why does this work? So let's do an analysis. So let's do the analysis of this. So what this really means is that, let's say if phi is not satisfiable, that is, we are talking about the no instance. So if phi is not satisfiable, then what our algorithm does is that it is going to do the step 1, and in the step 1 it's going to find an assignment A which with maybe satisfying assignment with high probability. That is something it does, but we're not going to blindly say yes or no based on that. So okay, again there is a lag on mhm. Okay, so what I'll do is I'll exit from this tab once and rejoin again. So okay, so okay, let's hopefully this works. Okay, so then what we're going to do in the step 2 is that we're going to evaluate phi on A, and if phi is not satisfiable, then clearly, because phi is not satisfiable, phi of A is going to say 0, that is, it is not satisfiable. In that case, we are always going to reject. So this is what our algorithm does. So I'll just show the algorithm once. So we did find an assignment which is satisfiable with a good enough probability, and then we checked whether it is actually satisfying. So we didn't rely on the fact that it might be satisfiable, we actually tested it, and now that it says because phi is not satisfiable, no matter what this A is, it's always going to say that phi of A is 0. Okay, so therefore we are always going to reject. So in this case, what will happen is if phi is not satisfiable, we are always going to reject with a probability of 1. So this does the main, this achieves the main thing that we wanted to achieve, that if x is not in the language, the probability that m rejects x is going to be 1. So this does the main thing that we wanted to achieve. Now we also want to ensure that in the process we did not it will not end up affecting the probability in the other case, that if x is in the line, that if it is indeed satisfiable, then we're going to be correct with a good enough probability. So how do we do that? So okay, so the main idea is going to be that we're going to so there are two things that we need to show. One is this two things. One is that how to find this assignment A, and second is the correctness or guarantee when P is satisfiable. So these are the two things that need to be done. So we'll quickly describe how to do this. So the idea is going to be that we're going to use the self-reducibility like we mentioned earlier. So what we'll do is we have this formula phi on variables, say n many variables. What we're going to do is that first set x1 to 1, and then ask our BPP algorithm, ask BPP machine whether phi of 1, x2 and so on up to xn is satisfiable. Okay, and with a good enough probability, it's going to say that okay, you are correct. Now I'll not stop here, we are going to amplify this. So instead of using, I'm not happy with the 2/3 probability here, we're going to amplify it k many times or n many times. You'll see why this amplification is needed, and then we will find out whether phi of 1 x2 xn is satisfiable with a good probability. So just 2/3 is not happy with that. We'll amplify it further and have a good enough confidence that with some probability, I'll call it p, we are satisfied. Okay, now in the next step we will replace x2 with a 0 or 1, and so whichever works, or we can try both and see which works better, and do the same thing again. So substitute, so at each step substitute or eliminate one variable, eliminate a variable xi by setting it to a 0 or 1, and in the next step what we are going to do is that we are going to amplify n times and repeat this until all the variables have been set. So at the end of this, what we will really get is an assignment A which is satisfiable with high probability, and this is where we are going to do the analysis and show that at the end we are correct with at least half probability. So this is some minor calculation that we need to do, which I'm going to leave for now. Okay, but okay, it is essentially the same analysis that we did earlier, the amplification analysis. What is the probability that we make an error? It is either we made error on all of them or n-1 many of them, and so on. So I'll leave that part for now. So just a small exercise to show that the error, or let's say that if x is indeed in the language, then probability that, or let's say phi is satisfiable, m accepts phi is with a good enough probability. So this is a small part that I'll leave for now, but to summarize, the main idea here was that we want to show that if NP is contained in BPP, then NP is equal to RP. So so this involves containment in two directions. One is that RP is contained in NP, This is something that follows from the definition. This doesn't even require the assumption. So this is something that we already know. So all that remains to be shown is that if NP is contained in BPP, then NP is contained in RP. Okay. And how did we do that? We used our NP complete language SAT, our favorite NP complete language, and we assumed that SAT has a BPP algorithm. This is what the algorithm guarantees. What we wanted, on the other hand, was an RP algorithm. So we want this accept probability to be at least half. But the major improvement that we wanted here was to get this 2/3 all the way to zero error. So we always wanted to be correct. So there were the main idea was that we're going to explicitly find a satisfying, not really a satisfying assignment, but an assignment that's satisfying with a good enough probability. So okay, so this is something that we did, and then we explicitly checked whether it does satisfy phi, and if it does, then we said we'll accept. If it does not, then we say we reject. Okay, and then we'll jump to the analysis part, where if phi is not satisfiable, then any assignment A that the step1 finds will evaluate our phi to 0, because phi is not satisfiable, so any assignment will not make it output a 1, and so in that case we always reject it. So we were correct with probability of 1 in this case. Okay, this is what we wanted to achieve. The other thing that we wanted to ensure was that in the process we don't end up changing this error probability of half. Okay, we don't end up increasing it. So how do we show that? So we defined our process of finding this A explicitly, which is basically our self-reducibility idea. Just that we're going to set our variables one by one to the boolean values of 0 or 1, and we're going to amplify it. So this is one step that we need to do to make sure that in the end we get our probability, a good enough probability. And so we use that same idea, setting the variable one at a time, amplifying it, and getting an assignment A which might be satisfiable with the high probability. So this is a small part, a very small calculation that I'm leaving out for now. Okay, but that was the major idea. Okay. Okay, so I'll skip this part. Okay. Okay. So I'll define one or two more classes. So I'll just these are very simple definitions, but are very interesting. Okay. So what we know as of now is we know the class BPP. We know what is P. I'm going to define two more classes. One is what is called PP. The other is what is called sharp P. So this stands for. So I'll define this. Okay. So what is the class PP? PP stands for probabilistic polynomial time. Okay, so what is the definition? When do you say that a language is in PP? So if X is in the language, then so there is a non-deterministic Turing machine M such that the number of accepting paths. So notice that when you have a non-deterministic Turing machine, you have several computational paths in the tree, and the idea is that if one of them accepts, then we will accept. It doesn't matter what the others say. If all of them reject, then we reject. This was the idea. So we'll modify this slightly and say that if, say, majority, so we'll look at all the answers on all this on all these paths. If the majority of them say reject, in this case that's what happens, we're going to reject. If the majority of them say accept, then we're going to accept. So if X is in the language, we want the number of accepting paths to be at least to be majority. So you want majority of paths to accept, and if X is not in the language, then we want the majority of paths to reject. Okay, so this is what it really means. Okay, so just to repeat, so when do you say that a language L is in BP? If there is a non-deterministic Turing machine that runs in polynomial time, and if X is in the language, the majority of the paths in its computational tree accept. If X is not in the language, then the majority of paths in the tree are going to reject. Okay, so first question is, you want to show that BPP is contained in PP. So this is really simple. So what you do is that we will let's say M is the or N is the machine for PP. What I'll do is okay, I'll just call it M again. What I'll do is that I'll run M on on input X, and it will tell me whether um, hmm, yeah, so it will tell me whether the majority of them are accepting or not. Okay, so with that I sort of know um, the first bit of the, so think of the number of accepting paths as a binary digit, and what it tells me is that whether this digit is 1 or not, because so I mean, just take a moment to think about this. So if this is the total number of accepting paths represented in binary, if the majority of them are accepting, this bit is going to be 1. If the majority of them are rejecting or not accepting, then this bit is going to be 0. Okay, so the idea is that we'll find out this count, what is the total number of accepting paths, if it's greater than 2/3 or whatever BPP is defined with respect to. If it's greater than 2/3, if the total number of paths is accepting paths is greater than 2/3, then we're going to accept, otherwise we're going to reject. So this is the basic idea behind it. So yeah, okay, so this PP can be thought of as a majority P. So because what it really does is that it finds the majority of them. So the fraction that we have here is half, whereas the fraction that we have here is 2/3. So okay, and okay, so for the next part, to show that P to the PP is equal to P to the sharp P, I need to define what the sharp P is. So I'll just define that. So what is sharp P? Sharp P is called counting P or sharp P simply. And what does it do? Well, if you say that a language is in sharp P, if there is a non-deterministic Turing machine M, which tells you the total number of accepting paths at the end. So there are several computational paths. It is going to write, so it's going to write the number of, or output the number of accepting paths on X. That's what it does. So the point is that you want to show that P to the PP is as powerful as P to the sharp P. Okay, so on one hand you have a very powerful machine which tells you the exact number of accepting paths. On the other hand, you have a okay, I mean it's obvious that PP is contained in sharp P, because this just tells you a majority. It just tells you some information about the total number of accepting paths. It tells you whether majority of them are accepting or majority of them are rejecting. Whereas what sharp P does is that it tells us the exact number. So it's plausible that sharp P is much higher, or at least higher in the hierarchy than PP, because if you know the answer to sharp P, you of course know the answer to PP. Okay, so that's the idea, and what you want to show is that P with Oracle access to PP is as powerful as P with Oracle access to sharp P. Okay, so the idea is again going to be similar. What you sort of want to do is that if the number of accepting and rejecting paths are written as binary, then this first bit is going to be something that PP tells us. If majority of them are yes, it's going to say yes, then this bit is 1, otherwise the bit is 0. Now we want to do some sort of a surgery to find out this other bit. So one thing that you could do is that you can sort of artificially pad some of the paths, add some more bits, and pad some of the um, uh, some rejecting or accepting based appropriately, so that once you have this value by once you have this entire value by, and you know that some x many of them were padded answers, you will find out what is the second bit of this. So this is some basic surgery that can be done to extract the second bit. Again, invoke a PP oracle for the second bit and find out whether it's 0 or 1, and then we're again going to modify this machine slightly and keep on asking, so that each time you get one bit at a time and you can find out the entire um, the exact value of the total number of accepting paths. So this is something that you can work on. So I'll leave this part. So this is a simple exercise to how do you extract the second bit and invoke the PP oracle again, and keep on doing this process. So okay. Okay, and I'll just these are like relatively simpler. So what this says is that, notice we had defined this when we defined oracles. So a to the b of k, what k denotes is the number of times, number of queries to oracle b. So this is what this denotes. So what this says is that np is contained in p to the sharp p with one query. So okay, so how do we show that? Well, what we simply do is that we're going to invoke our sharp p oracle, and that will tell us the total number of accepting paths. In one query, it's going to tell us the total number of accepting paths, and if this number, so let's say I'll call it k, if k is greater than 1, then we are going to accept, otherwise we are going to reject, because that's what our NP oracle does. So if the number of accepting paths is at least 1, then we're going to accept, otherwise we're going to reject. And what this number is something that this sharp p query tells us. Okay, and BPP is again similar. So BPP is contained in p to the sharp p with one query. So again, sharp p will tell us the number of accepting paths, and what we are going to do is this time check if k is greater than 2/3 of the total number of accepting paths, then accept, otherwise reject. So it's the same thing. In fact, you can think of defining several a hierarchy of classes where NP is somewhere here, which says that okay, if there is at least one accepting path, then I'm going to accept. BPP is somewhere here, or which says that if at least 2/3 of them accept, then we are going to accept. So you can think of defining different numbers and think of different classes, but yeah, and yeah. So the major ones that we are interested in are these. Okay. And okay, that brings us to the last question, which is okay. So I'll quickly give the ideas for all the three parts. So notice that we have this notion of L and P, where L is the set of all classes of languages that have log space um, deterministic Turing machine, and P is the set of all languages that have a deterministic polynomial time Turing machines. So we do know that L is contained in P, we don't know whether this containment is proper. And on the other hand, we have this class of BPP which have probabilistic polynomial time Turing machine that makes error on both sides. So we can think of an analog called BPL where so we'll say that the language is in BPL if there exists a probabilistic polynomial time Turing machine M, um, or sorry, it's not really probabilistic polynomial time, it's there is a probabilistic machine M that runs in log space, and the acceptance reject conditions remain the same. So if X is in the language, the probability that M accepts is at least 2/3. If X is not in the language, then the probability that M rejects is at least 2/3. So this is not something new. The only change that happened is that instead of allowing it to be a polynomial time machine, we are allowing it to be a log space machine. So okay, so this is the definition of BPL. Similarly, an analog of, so we saw RP machine where we have some accept reject conditions. You can think of a log space analog of it, which I'm not going to define. It's very simple, very similar. So just allow the machine to use log space instead of giving it a polynomial time. And yeah, so now you have this RL here and BPL here. These are the two analogs that we define, and we know that, so we saw earlier that we know that BPP is contains RP, that's by definition, and you want to show that BPL contains RL. Okay, so okay, so how do you show that? So we know that if you want to show that if L is in RL, then L is in BPL. This is what we want to show. So let's write out the definitions. If L is in RL, then if X is in L, then probability that M accepts X is at least half, and if X is not in L, then the probability that M rejects X is equal to 1. Okay, so this is something that we have assuming this right hand side that L is in RL. So this is the definition that we wrote down. What we want is a BPL algorithm. So what does BPL demand? BPL says that if X is in the language, I want this to be with a good enough probability. So I'm not happy with half, I want, let's say, 2/3. And here I'm okay with relaxing. So here I'm also okay with 2/3 probability. But in this case, we need a booster. So half is not something that we'll be happy with. So what do? The idea is very simple. We're going to use our amplification technique. So use the amplification technique. So it's enough to just use it once. So instead of running it twice, once you just, let's say, run M twice. So we're going to run M twice, and if M accepts, then once, then we're going to accept, or at least once. Sorry, it's the other case, right? So accepts at least once, then we are going to accept, and if M otherwise we are going to reject. Okay, so what will happen? The same analysis that we did. If X is not in the language, then both the runs will say reject, so we will end up rejecting. So the probability that our new machine rejects is still 1, which is at least 2/3, so this is fine. But if X is in the language, then we are going to accept if at least one of them accept. So when do we make an error? When both of them make an error. So first error happens with half probability, second error happens with half probability. So the error probability is 1/4. So the probability that m prime succeeds or accepts is at least 1 minus 1/4, which is at least 2/3. So okay, so that's something that we get. So this amplification is only needed to get this half boosted to 2/3. um, the other part remains the same, so this one is unchanged, so this is something that we still maintain. Yeah, okay, so that shows the first part, that RL is contained in BPL. Naturally, RL is also contained in RP, BPL is contained in BPP. So these are something that follows from the definition. The interesting ones are the part B and C, where the first one says that BPL is contained in D space of order log square n. So you can simulate this machine BPL using quadratic log square space. Okay, so we have seen a similar result earlier. So what we saw is that okay, what we saw is that the part B okay, sorry. So okay, again there is some flag in the display. Okay, I'm going to exit and reshare one more time. Okay. Okay. So the next thing that we want to show is that BPL is contained in D space of order log square n. Okay, and I just want to mention a similar result that we saw earlier today, which is BPP is contained in. Okay, I'll not. Okay, maybe I'll not. I'll talk about it later. So okay, so this is something that we want to show, and um, yeah. So notice that the trivial idea is not going to work, because we have when we go over this random bits, we really have exponential many of them. So this is 0 1 to the p, and these are exponentially many of them, so we can't really store, even if those were logarithmic, we couldn't have stored all of them and um, yeah, and simulated the whole thing. But but we've seen something very similar here, very similar to the statement that's written here. So we know that L is contained in D space of order log square n. So this is something that we've seen earlier. So the idea is actually going to be very similar. So idea is that we are at a start configuration, and from there are several possibilities that it could go to. There are several configurations that it could go to, and from there it just branches from there. So this is the, you can think of this as a configuration graph. And when do we say that we accept? If at least 2/3 of them are going to lead us to the accept configuration. So instead of going serially over it, which will take large amount of space, because the path, the depth of this tree could be very large. So the idea is very similar. The idea is that we use the recursion strategy. So use the recursion strategy and see that you want to find out whether there is a path from the start configuration to the accept configuration in um, say k many steps. Then there must be then you're going to sum over the probability, so you want to find out this probability. Okay, then there must be some way that you go from S to a configuration, say L, in k by 2 steps, and from L to T in k by 2 steps. So what this really boils down to is the probabilities from whether there's mm, okay, and the probability that there's a path from L to T in k by 2 steps, where T is our accept configuration and S is our start configuration. Okay, and we're going to do a U. So we don't really know what this L is. So L could be any of the states, any of the Q states. So we're going to do a union over all of this. So okay, and then the idea is that we're recursively going to use the same thing. So find out this by recursive strategy, find out this by recursive strategy, and calculate this probability. So if the probability eventually is greater than 2/3, then we will say accept, otherwise we'll say reject. So we know that the depth of this recursion is logarithmic, therefore this algorithm will act. So the analysis of this log square n is exactly the same that we had earlier. So the depth of the recursion is log n. Each of the iterations may take up log n space. So altogether this is an order log square n. So this is exactly the same analysis. The only difference is that now we are dealing with probabilities. So this is no longer a deterministic machine, it's a probabilistic machine. So we are actually calculating the probabilities, and at the end, if this sum is going to come out to be at least 2/3, then we're going to accept, otherwise we're going to reject. So this is the only difference, but the rest of the analysis remains the same, so I'm not going to go into the details of that. Yeah, and the third thing is to show that finally BPP is contained in P. To show that BPP, sorry, this is, BPL is contained in P, yeah, is contained in P. This is part C. So I just want to bring up the obvious approach here. So earlier we saw that BPP is contained in P space. This is something we saw. How did we do that? Well, we just did a simulation of BPP machine using the deterministic idea, that is, go through all random bits here. So this part was dedicated to the random bits, this part was for the simulation, and this was for the count. Okay, and we said that this going over all of them, this is going to take polyspace. This run is going to be polyspace because it's a deterministic polynomial time machine. It's a polynomial time machine, right? So it can only take polynomial with space, and the count is also bounded by polynomial, and then we reuse the space. Okay, so this is something that we saw just now, and therefore we showed that this is contained in BPP is contained in P space. But the same idea, so instead of P here you have a logarithmic space, and you want to show that it can be done in polynomial time. So the same idea cannot work here because yeah, for the simple reason that you don't have this nice random this space, that polynomial much space that you had, you don't have the space to store that, so you don't have a nice way to iterate over them. So this approach fails. Okay, so like some simulation sort of a thing cannot be done, so you need some more insightful idea to to get there. So what do we do? I'll just describe the proof idea. Okay, the proof idea is that we know that M is a since L is a BPL, there is a probabilistic polytime machine. Okay, and what it does is that if we look at the configurations of, so let's say these are all the configurations. So these are C mini configuration, S is the start configuration. Okay, and okay, again there's some lag. I'll wait for the display to refresh. Okay, so we have this. Okay, so what we write in this matrix is the probability that from this configuration we go to this configuration. So for example, maybe the probability that I go from start configuration to this configuration P is half, and some R is half, and so on. So this is going to be a matrix that's filled with fractions. The fraction denotes the probability that you go from a state S to state I to state J. So yeah, okay, and yeah, so then okay, again there's some lag, so I'll maybe write this down and say it orally for now because there's a lag in the display. So okay, so the idea is going to be that we're going to look at this matrix and observe that if you, okay, there are 2-3 ideas that are involved here. If you okay, so if you go from matrix A to matrix A square, and say in general to A to the K, the ijth entry of A to the K denotes whether there is a path of length K or at most K from I to J. Okay, so this is what it denotes. So this is a simple, it's a nice idea that you can work out. So this is a known fact, and the proof of it is also not very difficult, and it's also a very useful fact to know. So this is what it denotes. And what do I want? I want to find out whether I can go from the start configuration to the accept configuration. Okay, this is something that I want to find out, and K denotes the number of steps that I'm going to use in the process. So the idea is again similar. You're going to have to simulate this matrix multiplication again and again, and find out this particular entry. If that entry says greater than 2/3 at the end, when we have reached the accept state, then we're going to accept, otherwise we're going to reject. So the main idea later on is going to be to simulate this. So I'll try to write this up properly, but I just wanted to convey the 2 ideas. So I guess I might have said it in a hurry, but I'll maybe I'll try to write this out, or write some solution for this. But this is the major the main 2 ideas that are needed. You can also try to work this out, and next we will meet on Saturday, 10 a.m. to 12 p.m. Yeah, and we'll discuss about circuits, more on circuits. Okay, so okay, I'll leave the call.